So let's talk about one of the weirdest puzzles in modern AI. It's a phenomenon that completely flips the script on everything we thought we knew about building good machine learning models. And it all starts with a really simple but kind of radical question. For years, the rules for building AI seemed pretty clear-cut. But what if the secret to creating more powerful, more accurate models was to do the exact opposite of what the rulebook told us? That's the mystery we're diving into today. To really get why this new discovery is so wild, we've got to first go back and understand the old way of doing things. You see, for decades, there was this time-tested classic recipe for building a good AI model, and it was all about finding the perfect balance. At the very heart of this old rulebook was a concept called the bias-variance trade-off. Honestly, the best way to think of it is as a constant tug-of-war. On one side, you've got models that are way too simple, and on the other, models that are way too complicated. The whole goal was to land somewhere right in the middle.
So what happens if you get that balance wrong? Well, you hit one of two extremes. A model with high bias is underfitting. It's just too simple. It's kind of like a student who barely studied for a test. They can't even get the basic concepts down. Then you have the other side, high variance or overfitting. This model is so complex that it memorizes the training data perfectly, including all the random noise. This is like the student who didn't learn the material, they just memorized the exact answers from the study guide. The second they see a new problem, they're lost.
This chart, this was basically the Bible for machine learning for a long time. It shows the U-shaped curve of error. You start with a simple model on the left, and your error is high. As you make it more complex, the error goes down. Great. But if you keep going, making it even more complex, the error starts to creep back up as the model begins to overfit. That little dip at the bottom, that was the holy grail, the sweet spot.
And yeah, that was pretty much the whole game. For decades, the goal of every practitioner was to carefully tune their models, add a little complexity here, take some away there, all just to land right at the bottom of that U. It was the only way you could build a model that actually worked on new data. Or so we thought. And then things started to get, well, really weird. As deep learning models got bigger and bigger, researchers started noticing something strange. These new models weren't following the rules at all. The real world wasn't matching the textbook anymore. What's wild here is the sheer scale we're talking about. The models that power things like ChatGPT or DALL-E are what we call over-parameterized. This means they have way more internal knobs to turn, parameters, than actual data points to learn from. Now, according to the old rulebook, these models should have been complete, catastrophic failures. So this was the million-dollar question, right? If that trusted U-shaped curve was correct, these enormous models should be so far off to the right on the chart that their error rate would be through the roof. They should be the worst case of overfitting in history. But they were, and still are, the most successful models ever built. What was going on? The answer, it turns out, was a new map. That U-shaped curve wasn't wrong, it was just incomplete. It was only the first half of the story, so say hello to the double descent curve. Let's break this down. In that first part, the classical regime, everything behaves just like we expect. The old U-curve works perfectly. But then you get to a point where the model is just complex enough to fit the data, and something bizarre happens. The error suddenly spikes up. And then, after that peak, in the modern, over-parameterized world, the error starts to go down a second time. That crazy spike has a special name, the interpolation threshold. This is the exact moment, the tipping point, where a model has just enough capacity to get a perfect score on its training data, to perfectly memorize every single example it has seen. You'd think this would be peak overfitting, the absolute worst place to be. And for a brief moment, it is. All right, let's trace this whole journey from start to finish. You start on the left, you add complexity, and the error goes down. That's our first descent. You hit that classic sweet spot. But if you keep making the model bigger, you hit the interpolation threshold, and bam, the error skyrockets. But, and this is the incredible part, if you push past that peak and keep adding even more complexity, the error begins its amazing second descent, often dropping even lower than the original sweet spot ever was. So the crucial question is why?
why on earth does making a model even more ridiculously complex after it has already memorized everything suddenly make it better at handling new stuff? Well, the secret lies in having an abundance of options.
You see, once a model is past that interpolation threshold, it's so powerful that it doesn't just find one way to get a perfect score on the training data. It can find thousands, millions, maybe even an infinite number of different solutions that all perfectly memorize the data. The real question then becomes, out of all those perfect solutions, which one does it actually pick?
And this is where the magic really happens. It's not just the model, it's the training process. The algorithm we use to teach the model, often something called stochastic gradient descent, or SGD, it acts as a tiebreaker. It turns out these algorithms have a sort of hidden preference, what we call an implicit bias. When they're faced with countless ways to get a perfect score, they naturally gravitate towards the one that is, mathematically speaking, the simplest or smoothest. And that smoother, less complicated solution? That's the one that just happens to be way better at generalizing to new data it's never seen before.
So look, this whole double descent thing isn't just some weird, nerdy trivia. It's a game changer. It fundamentally rewrites the playbook for how we should be thinking about building powerful AI systems today.
So, what's the bottom line here? First, that classic U-shaped curve we all learned, it's only half the story. Second, for a lot of today's most important models, being too big by the old standards is not a bug, it's a feature. It's key to their success. And finally, this whole amazing phenomenon relies on these subtle, hidden preferences of the algorithms we use to train them.
What this all means is that the old wisdom, the idea of spending all this time meticulously searching for that one tiny sweet spot, is kind of being replaced by a new, totally counterintuitive strategy. For many big modern problems, the best approach might just be to throw caution to the wind, build the biggest model you possibly can, and let that second descent work its magic. The discovery of double descent proved that some of our most fundamental ideas about AI weren't quite right. We solved one huge mystery, but it just blows the door wide open to so many more questions. You know, if a rule as basic as the bias-variance trade-off had a secret second act, what other rules are we following right now that are also just waiting to be broken? What's the next big thing we've got completely wrong?